In the name of God, the compassionate, the merciful, Engineering Plasticity, Chapter 3, Yield Criteria, Part 3. Let's go back to this cylinder, this yield surface. Obviously here, for the sake of simplicity and introducing two yield criteria, which are Tresca and Mises criteria, I have taken the yield loci or locus as a circular locus, and also, as you can see, as this hexagon. This hexagon is Tresca, and this circular surface is the Mises. So the circular surface along this hydrostatic line, we continue this and we get this cylinder, okay, circular cylinder, and Tresca also we continue these lines along parallel to the hydrostatic line. These lines parallel all these lines, okay. So we get a hexagonal shaped cylinder for the Tresca. So Mises and Tresca are the most two popular yield surfaces. Of course, we have many yield functions, different yield criteria, but these are the most popular yield criteria, and we are going to talk about them. So, if we have a state of stress P, OP like that, then ON would be the hydrostatic component and PN would be the deviatory component, and it's not yielding. But if it reaches there, it will yield. If it reaches here, yields. If it reaches here, then it yields according to Tresca, but it will not yield according to Mises. We are going to talk about this a little bit. Now this image, which I have chosen from the previous chapter, the stress analysis chapter. Okay, here again we are showing sigma 1, sigma 2, and sigma 3, and this triangle ABC, as you can see, is makes equal angles to the three axes, and this line which goes through the center of this triangle like that, this center line makes equal angles to all three axes alpha. So this is the hydrostatic component of the stress, like that line, and this plane is perpendicular to that line. So that is the deviatoric plane, like that. This is the deviatoric plane. So in here we have just shown the scales that if we have a line like that, OB, then O prime is that, O prime, and O prime B is on the deviatoric plane, like NP. Okay, so if we draw that, we will see that if we take this 1, then that is root 2, and this is root 3. Okay, so that's alpha and that's beta. And that is the proportions of these scales. In other words, if this is a component of a stress, which is, supposing it is a component of a stress, OB is a component of a stress, then O prime B is its deviatory component, and O prime is its hydrostatic component. And then there is a relationship between these components like that. So sigma 1 prime is the deviatoric component of the stress, which is this one, or NP, and is equal to sigma 1 cos beta. So this one is, okay, that is sigma 1. That is the deviatory component, sigma 1 prime. So sigma 1 cos beta is this component, which is sigma 1 prime. And because of the proportions of this triangle, cos beta is root 2 over 3 times sigma 1. Okay? So if you have a component of stress reaching the yield surface, then this OP, for instance, would be the state of stress, general state of stress, and that would be the deviatoric. The deviatoric would be root 2 over 3 times sigma 1. Therefore, there is a number which scales down sigma 1 to sigma 1 prime, because we said sigma 1 prime is the component which causes the yield. So we could use this as a scaling down. You can see it as like this. If we have this component of stresses sigma 1, sigma 2, sigma 3, we want to scale them down on this deviatoric plane, then we just multiply it by this scale factor root 2 over 3. Okay, similarly for sigma 2 prime, we have this, because it's the same triangle all over. The proportion is the same, because this O edge makes the same angle. Okay, 1 over root 3. In other words, it means that this scaling factor scales everything in the three-dimensional space of stress into the two-dimensional deviatoric plane. So everything in the three-dimensional stress space that we want to project into the deviatoric plane, we just multiply it by root 2 over 3 to scale it down, okay, to scale it to the right size. And then we have these three components of stresses on the deviatoric plane, which are proportional to sigma 1, sigma 2, sigma 3, and that's the proportional constant of proportionality, okay, root 2 over 3. So we use this in the next slides. Now then, direction cosines of OH, as we mentioned before, cos alpha, cos beta, and cos gamma are equal. Cos alpha, because alpha is equal for all of them. So cos alpha, cos alpha, cos alpha, 1 over root 3. Here we can say Pn squared is equal to OP squared minus ON squared, okay? That's the OP squared minus ON squared equal to Pn squared. That's what we said before. We said that the component, we said that the stress is equal to, or the component, deviatoric component of a stress is equal to stress minus the hydrostatic component. Obviously, that is in vector form, but if you want the in scalar form, we show it like that. Now, what is OP? OP2 is sigma 1 squared. Okay, that's tensor notation. Sometimes we show it like this. Maybe you are not familiar. You are familiar with showing the tensors with I and J, but we show with 1, and it means 1, 2, and 3. Sigma 1 to the power of 2 over 3, and this is what this is a notation anyway. We get this. So why we wrote that? Because OP3 is the general state of stress. That's the general state, and that is the hydrostatic component of stress. So that is what we get. That's what we had before. Okay, that's what we had before, and we could write it in this form as well. Sigma bar squared equal to sigma 1 minus sigma 2 to the power of 2 plus sigma 2 minus sigma 3 to the power of 2 plus sigma 3 minus sigma 1 to the power of 2, that is the summation, and is equal to 2y2 because y is the yield strength in the uniaxial tension. So because this is the yield criteria for all kinds of loadings, so it should be true for the uniaxial loading as well. For uniaxial loading, sigma 2 and sigma 3 are 0. Sigma 1 here is equal to y, and that's why we get this 2y2 here. And I want to show you this slide to prove, to show that why the hydrostatic stress does not have any effect on the yielding. This is the hydrostatic stress, sigma m. You see, the size of the Mohr circles have remained the same. When we increase the hydrostatic stress, the Mohr circle moves on this axis. Okay, this Mohr circle was here, the hydrostatic stress was this. Okay, now we have moved it from that point to there, so we have increased the hydrostatic stress, but the Mohr circles sizes remain the same. That's why we say that yielding is not affected by the hydrostatic stress, because it does not, the Mohr circle does not grow. It remains the same, only it translates from one point to another point. Okay. Here again I have shown you the yield cylinder, and that is the Tresca yield surface. As you can see, this is the von Mises yield surface, and that's the we call this pi plane because it's situated at point O, and deviatoric plane, of course, and sigma 1 plus sigma 2 plus sigma 3 is 0 here because it is at point O. Okay, and that's the line of hydrostatic stress where sigma 1, sigma 2, sigma 3 are equal, and this line makes equal angles to all three axes. Here I just show you line OP is the line, is the stress vector, and it's just on the surface, on the yield surface, and it means that the material starts yielding. And that's its OO prime, its hydrostatic component, and that is the deviatoric component. Okay, and so these are, if I show O prime P on this pi plane, that would be the deviatoric. O prime P will be some lines parallel to that, like that. So that will show the state of stressful yielding, and we show it by, and if we take these lines and see their projections on the pi planes, then we get sigma 1 prime, sigma 2 prime, sigma 3 prime, which are all we showed before, that they multiplied by this scale factor, we get this sigma 1, sigma 2, sigma 3 prime. And now OP prime, which is the deviatoric, which is equal to O prime P, is equal to OP cos beta. Again, as you can see, this is multiplied by the same scale factor, because all the components are multiplied by the same scale factor. Therefore, the OP, we want to project it on the pi plane as OP prime, is multiplied by the same scale factor as we have done for the component of the stresses. Okay.